Hello folks, this is Tom from anti-proton.com, and today I've got my CDV700 with me, my trusty CDV700 with an original sounder on it. I'm going to be talking about sodium-22. Now, here is sodium-22, right here. Sodium-22, see if I can put this in where you can see it. Focus, 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 focus. Focus. Focus, focus, focus. Okay, it's not going to focus worth anything. Sodium-22, this is 37,000 decays per second of the material. Sodium-22 is a beta-positive emitter. Beta-positive means this is an antimatter emitting material. This is producing antimatter, like Star Trek warp core, you know, antimatter, that sort of thing, antimatter. All of the time, this is producing it 24/7. Right now, it is shooting out antimatter in all directions, including through my hand. Oh well, switch hands. But basically put, this guy right here is slowly turning into neon-22, which is harmless and inert. You find neon-22 in things like neon signs, although they don't get neon from this, but it is turning into neon. It's a pretty potent beta emitter. In fact, let's put it over here on the table. And we'll put the I keep calling it a ludlum, put the CDV700 near it. We're in the times 10 mode right this second, times 10. So that's 0, let's see, 0, 1,000, 2,000, 3,000 counts per minute. Goes off the chart. Times 100 mode, so 0, 10,000, 20,000, 30,000. So 30,000 counts per minute. It's about 5,000 counts per minute. I bet you the Spectre will get a different read on it though. $54,000. Not bad. Thank you, Inspector. 54,000 counts per minute, which is much lower than some of my other isotopes. So, let's talk for a second about sodium-22, and let's talk about what it does. It has a half-life, it says right on here, of 2.6 years. Half-life of 2.6 years. So, 7 times that, and it'll be nearly gone. So, let's see, let me do my math quickly. 2.6 times 7. In about 18 years, this sample will be very useless to me in about 18 years. Anyhow, I have a Gamma Spectacular. This is my B Research Gamma Spectacular with my CDV logo on it. It's not my CDV logo, it's a not CDV, it's not CDV, Civil Defense. I'm like screwing my words up today. This is a Civil Defense logo. It's not mine, it is the Civil Defense logo. I own the, you know what I mean? I'm not trying to take ownership of it. You know what I'm saying? I'm screwing stuff up today. It's pretty bad. Anyway, I have a Ludlum 44-2 sodium iodide detector. This is a 1-inch detector, sodium iodide. It's not the best detector for this type of particle, not particle, but this type of isotope, because the energy, well, there's a lower energy, but there's also high energy, so, you know, and don't worry about the spectrum. It's actually a composite of a couple spectrums. Just kind of ignore it for right now. We'll get to it in a minute, because I'm going to start it over again. I'm going to do the whole thing for you now. So let's talk about what this does, and then let's actually calculate the spectrum. Sodium-22 decays to neon-22 by 2 methods. It either decays by electron capture 10% of the time, and what happens in electron capture, and I'm going to spare you the quantum details, I'm going to give you kind of an analogy. Electrons floating around really, really close to the nucleus. Sometimes they accidentally get a little too close and they go boop, right into the nucleus. Yeah, that's not really the most scientific explanation, you know. Boop. But they get sucked into the nucleus, and that gives the nucleus enough energy to transfer one of its protons to a neutron, because there's too many protons in this atom, basically, way too many protons. It's not stable, if you like, in a quantum chromodynamic sort of way. The actual nucleons in the center of the nucleus, the protons and neutrons, the ratios are not right. There's just way too many protons, and that extra electron gives it just that little kick that it needs to jump to neon 22 by converting a proton, which is a smaller particle, to a neutron, which is a bigger particle. And it emits a positron as a result of that. I believe electron capture emits a positron off the top of my head. I'd have to double check. I'm 99% sure. But my brain's like failing me today because I haven't had enough coffee. The other method that it uses is, there's nothing in the detector right now. It's just picking up stuff that's nearby. The other method it uses, and it does this about 90% of the time, plus or minus, is something called beta positive emission. Now you know beta negative occurs when a big heavy neutron decays into a lighter proton because there's too many neutrons in the nucleus, and the surplus extra mass gets sent off as a W negative particle, which is a short-lived virtual particle. It's so short-lived it's called virtual, and almost immediately that W negative decays into a electron and a positron. It shares the energy between the two of them, and they go flying off and they get detected. Like, for example, cesium-137 does it that way. But that's not how sodium-22 rolls. Basically put, what happens in this case is neon-22 is a very energetically favorable configuration for the nucleus. There's a nice ratio going on there. Very, very crappy ratio of protons and neutrons going on in here. And it is energetically more favorable. It'll be lower energy, a lower energy state to drop to neon-22 than to remain sodium-22. It's a lower energy. And so there's a tiny chance that what can happen is the atom can actually, it's not really a tiny chance, it does it all the time, the atom can actually emit a W positive virtual particle via something called the weak nuclear force. It's actually the unified electrostatic weak, but it'll shoot out this big W particle, and it'll drop itself down to the more energy stable neon-22. Even though there normally wouldn't be enough mass to turn a proton into a neutron because the proton's lighter, because it's more energy favorable, it can actually drop down. And that big, heavy W positive particle will quickly decay, because it only lasts the tiniest little fraction of time. That's why it's called a virtual particle. It will decay into something called a positron, which is basically just an anti-electron. Most particles are just called particle or anti-particle, the same name, whatever the particle is, you know. But positrons were discovered a long, long time ago, and they were actually given the term positron before we started just calling everything negative or positive. So they're positrons, and basically it's an anti-electron, and they go flying off with a regular neutrino. So anti-electron produces normal neutrino, but in beta negative you get normal electron and you get an anti-neutrino. They flip. Isn't that weird? Now, the positron will go flying out from either electron capture or regular beta positive decay, and it hits a free roaming electron. And when it hits a free roaming electron, the two of them come together as antimatter, like in the Star Trek reactor. Bam! They come together, and you produce an antimatter explosion, which produces 1,022 kill electron volts, 1,022,000. So if you like million, 1,000 thousands of million. So 1.022 if you like million electron volts of energy. And this emits two gamma rays. These gamma rays go fly in two different directions. You have each of them is exactly half of that amount of energy. So one of them is 511 kilo electron volts, and the other one's 511 kilo electron volts. And the detector will either pick up both of them, depending on the direction they shoot off or where they go off, or it might only pick up one. In fact, most of the time it only picks up one. So you're going to see a big 511 keV peak and a very, very tiny 1,022 keV peak. Now, we understand how that works, maybe, sort of, kind of, maybe. So here's what I'm going to do. Let's put away my detector, whose name is Melwyn, Scottish word for honeyed. And what we're going to do is we're going to take cesium-137. We have the detector set for 800 volts positive, and we're using PRA software, so we're good to go. We're going to take the little testing tray, stick the cesium-137 in it. We have a piece of aluminum to block the betas, so we get a nice clean spectrum. We are hooked up, powered on, ready to rock and roll with power coming out of the detector. Oh, well, sorry. USB is producing power to the actual gamma spectacular. Sound is then coming back and going into the detector to be measured by PRA, and we have a connector going to the actual sodium detector. See, we're already adjusting ourselves, so let's put the source in. We're going to start this thing over again and calibrate the cesium-137 really, really fast, and I'm not going to go into the details of that because we're going to go right into the sodium right afterwards. And you're not going to see it because we're going to be looking at the screenshot of this, but immediately after I get done with the cesium-137, I'm going to pull it out. I'm going to put in the sodium-22 like this, and I'll tell you I'm doing it. Stick it back in just like that, and that's what's going to end up happening, okay? So let's now take a look at the spectrum. Alright, so we started with the cesium-137 calibration, and here's cesium-137 fully calibrated, and now we're going to test the sodium-22. Now if you look at the cesium-137 calibrated sample here, I've already selected ROIs, which are regions of interest. This one right here is around 32 kilo electron volts. This comes from the X-rays from cesium-137, technically from barium-137. And this right here is the primary photo peak from cesium-137, technically barium-137M if you want to be technical. You should watch my video on cesium-137 to know what I'm talking about. But anyway, via this isotope with two valid points where energy is connected to a channel, I was able to then go up and enter their information, for example, the mean, the standard deviation, and the energy. See, here they are, the mean, the standard deviation, and the energy. When I did it, of course, I did it without energy calibration engaged. So you see there's a mean 47, I have it at 46. It's pretty close. Okay, so our calibration is pretty close. Let's just update our calibration a little bit. So 47.036 looks about right. There we go. And let's double check this guy over here just to make sure it's right. Mean is 2.94. Pretty good. Okay, good. Standard deviation's pretty close. Okay, so we have our calibration done with the cesium-137. It's now time to put the sodium-22 in. So let me clear the I said clear the spectrum. There, cleared it. Let's put the sodium-22 in the detector. And you can't see me doing this part, but just trust me, I'm doing it. With the shield up and everything. Let's put the cesium away so it doesn't interfere. And we'll start the spectrum now. Now, what interesting mysteries will sodium-22 produce? Let me put my mouse over the ROI and hit the delete key to get rid of them. Well, it looks really different, doesn't it? Let's come back in about 10 to 20 minutes and see what it looks like, and we'll pick out the features of sodium-22. Okay, well, we've run this spectrum now for 698 seconds, 700 seconds, so about 10 minutes plus or minus. Let's go ahead and set energy back again. And as we can see, this is an interesting spectrum. It actually looks different from the cesium-137 spectrum. You'll notice a couple interesting things. First off, this humongoid peak right here. What could that be? And there's some other little interesting peaks right here too. And then there's this thing and that. So let's get into what these guys are. First and foremost, if you might remember from the cesium-137 video I did, this right here is lead fluorescence. We will hit the B button, move our mouse over here, and hit the E button for beginning and ending a region of interest. This is beta particles slamming off of gamma rays and X-rays slamming off of the lead and causing fluorescence, X-ray fluorescence, fluorescence in the X-ray spectrum. And this fluorescence gets picked up at 75 and 80 kiloelectron volts plus or minus, about right there. This right here is actually a Compton continuum. You have a backscatter peak and you have a Compton edge. You can kind of see that this goes up and then it's got a kind of a shape to it. I don't know how to explain it exactly. Let's begin here and end about, oops. Let's begin there and we will end about here. This whole thing is pretty much Compton scattering. So basically photons are hitting the crystal and bouncing backwards completely or at various angles up to and including backwards. and that generates this guy right here. You typically find one of these sitting right after a primary photo peak. So that brings up a question, what's this? First off, let's stop data acquisition. Let's put our mouse here and hit the D for begin, and then put our mouse over here and hit E for end. This is the primary photo peak. It should be around 511 kilo electron volts. Let's see, 540, so the calibration's off a little. We can recalibrate this just a bit. Let's do that now. Let's say that, oops, let's recalibrate ourselves quickly. Let's go over here and cut off energy units. Never calibrate with energy units on. Okay, so the mean for this guy right here, the mean is 38.559. The standard deviation is 2.015. And the energy is, we happen to know, 511 keV, and I'll explain why I know that in just a second. Use energy calibration. Okay, so put that in there a little better. Pretty good. Now, what we have here are the positrons actually being emitted, because this is a beta positive emitter. The positrons, which are basically electrons that have a positive electrical force, they are actually annihilating with each other. They are antimatter. They are annihilating with free electrons and producing a photon, two photons in fact, one at 511 keV and another one at 511 keV. Typically these photons are going in different directions, and one of them will get absorbed and the other will usually not in a crystal the size I'm using here. So that's why we have the one photo peak here. Technically you could have another photo peak that would form for both of them put together at 1022 keV. There, I got rid of that blasted fan that was driving me nuts. It was making a lot of noise. Alright, so this guy right here, you might be interested because we have two more of them here. This guy right here, let's hit the B button for begin and the E button for end. This right here is actually a peak caused by the two photons from annihilation both being picked up. So yeah, we have like a little antimatter reactor going on right here. This calibration's off a bit, so let's change the calibration to be right. Get rid of energy units. This crystal that we're using, this Ludlam crystal, is perfectly good, but it does not like high energy stuff. Things over 800 or 900 keV become a problem for it because it's a smaller crystal. It's only a 1-inch crystal. I should have used a bigger crystal for this. And that's okay. But just understand that's why the calibration, it's very non-linear, the calibration. It's getting a little off here. So let's put in our mean of 66.6. It's about 6.599. Standard deviation is 0.681. And the energy over here should be, on my chart I have it listed as 1274.53 kiloelectron volts. That's about right. Technically speaking, I would think it would be at 1022. And I'm not actually sure what the extra little bit of energy is for. I'm going to have to look that up a little bit later. But anyway, that's okay. So let's click the button here. Let's use energy units. And that's throwing that calibration off. Let's switch to fit slope. See if that does a better job. Giving us a bunch of trouble. It's giving me some troubles today. Here, let's get rid of the 511 and see if it likes it. It's giving me some interesting troubles with my calibration today. Well, it just will not give up. It will not allow that energy to be where it's supposed to be at 511. I can't do anything about it. The machine's being crazy right this moment. I'll figure it out later. But anyway, this guy right over here should be right around 1,274 kiloelectron volts. This should be around 511, almost on the dot. These guys right here are going to be around
200 to 300 kiloelectron volts, and this guy right here is about 75 to 80 kiloelectron volts, and that is sodium-22, our favorite antimatter emitter. So that's also a good reason why you should use a bigger crystal. Lead crystal is perfectly good. I recommend the crystal that you actually can buy from the Gamma Spectacular guys from B Research, because they actually have a bigger crystal, like my bigger lab crystal, which, as I said, I would have used, but I couldn't find my extra BNC cable, so oops. This has been Tom from anti-proton.com, and bye-bye.